Good morning, everybody, and welcome to our third instance of the Code of the Month of CASTIEL. Today, we are happy to present you the code in nekRS, which is used by the Center of Excellence CoEC. And we have two presenters today. The first one is Stefan Kerkemeyer from Argonne National Labs, and he's the lead of the NEC project, so coordinating the development of the NEC family of codes. So very welcome, Stefan. And our second presenter is Mathis Bode from Jülich Research Center. He works in CoEC and is a focus and is deeply involved in the exascale ambitions of Jülich Research Center and this Center of Excellence. So please, Stefan, the floor is yours. First, one thing you can have, so the audience can, of course, have questions. We have a Q&A session after the talk, so you can just enter your questions either in the chat or there's a specific question area also in your panel, and we will answer them as they come in. So now, please, Stefan, the floor is yours.
Thank you, Guntram. First of all, thank you for the opportunity to talk about the NEC project and our latest solver called nekRS. So let me start with an overview about our project. So it started in the mid-80s at MIT, and kind of our mission was always kind of push the boundaries of fast and accurate CFD. Applications range from thermal hydraulics, renewables, combustion, and many more. We're an open source code with base funding from DOE. We're about a cross-functional team of 10 people. Our community is more than 500 users worldwide, mostly in discovery science, and there are about like 40 publications per year. And we have been part of several big research projects in the US and in Europe, namely CoEC, but also the new one, CEEC. And there are also various industry collaborations, mainly in nuclear engineering. So our work has always been driven by HPC. And after like 30 years, we start to see a new disruptive change, what I coined, the specialization era. So in other words, we're using accelerators, which can hopefully, accelerate our simulations. But it's a disruptive change, and as a response to that, DOE launched in 2016 the US Exascale Computing Project, which tries to push the performance on all fronts to higher levels, and obviously making sure that the whole ecosystem is ready for this kind of new technology. We're part of ECP through a co-design center called SEED, which targets exascale discretizations, and it's quite a big project involving 2 research labs, 5 universities, and more than 30 researchers. nekRS has been an outcome of SEED. It started as an early fork of libparNumL, which is kind of Tim Warburton's fast prototyping code. And for those of you who don't know Tim Warburton, I mean, he has quite some expertise in finite element and in particular on GPUs for more than now 10 years. So we thought, why reinventing the wheel? Let's start with libparNumL, strip out the parts we need, and go from there. Now, obviously, this is quite a radical change because we had this other code, our previous generation code called NEC 5000, which was a Fortran one, and now it's a code in C++. But we try to keep the user experience as smooth as possible, and it still solves obviously the incompressible Anomac number Navier-Stokes equation. We're still using MPI for distributed computing, but now there is this component X, which is the accelerator or the CPU. So the code is not just limited to GPUs, you can also run it on CPUs. And our abstraction for this is called OCA. I'll come to that in a second. We auto tune across the entire solver stack, and it's using high order spectral elements in space. And it supports various models for moving the mesh, deforming the mesh, conjugate heat transfer, Lagrangian phase model, turbulence models. And all this is available under our GitHub organization. And as I said, it's open source. So for those of you who are not familiar with spectral elements, here is just kind of a very short introduction. The idea is you solve the weak form of your conservation equations, and you partition your domain in E unstructured high order elements. Within each element, you express the trial and test function as an nth order tensor product. Usually the polynomial orders is a user input, and they range from 5 to 9 for most of our applications. And it comes obviously with some nice discretization properties, meaning it features low dissipation and small dispersion errors, which makes it really attractive for DNS and LES simulations. And thanks to the hardware trends, we can also evaluate these operators real fast because they're matrix free, and the work only scales with n, where n, which is the polynomial order, and n is the number of grid points. So there's only this n overhead, but you can still do this very fast. I'll show that in a second. The other nice thing is obviously you're way more accurate than compared to a low order method. And that's the whole reason why we sort of use a high order method. And here are 2 examples. And in both of these examples, you need about 8x less grid points for the same accuracy. Obviously, it depends what is the quantity of interest. So the 8 is not a universal factor. It all depends on what you're interested in at the end of the day. But here, these are basically mean quantities. If we would start to look into high order statistics, you may see even more than a 16x. Well, being accurate is one thing, but how expensive is it? And I also claim that you can implement this high order operator really efficiently. And here's kind of a demonstration to that. Here we compare in a simulation campaign we ran on Summit, our code nekRS versus another co-design center called AMR Wind. And it's using a second order finite volume code. And obviously, a lot of things kick in here, so you cannot really directly compare the two and draw any conclusion just about the spatial discretization. But still, you get sort of an idea, and you can see we're constantly faster than this other code. And part of it, and by the way, here we're using the same number of grid points. So this chart is really to say, hey, even if you use the same number of grid points, there is no extra overhead coming from the high order method, meaning the cost per grid point is competitive, if not even lower to the low order method. Now there's no free lunch. So obviously, these high order discretization schemes come with some challenges. And obviously, they don't just exist for high order methods. I guess all of them are also there for low order methods. But I guess one difference is that the community has more than 40 years experience in low order methods. So we know how to deal with these kind of challenges. While the high order methods, I mean, they have been around for a while, but I don't think it has been investigated to that detail compared to high order methods. So some of them are still work in progress or research topics. Not that there are no solutions to this, but yeah, they're challenging. The other thing, if you talk about emerging architectures, obviously you also have to think about how do you implement or integrate these accelerators into your code. And unfortunately, it's a fragmented mess. There is no golden standard. I mean, there are many vendor-specific languages, programming models around, other open source projects. And that's obviously something you need to address one way or another. In our way, we decided to use another product, another code of the seed project, which is called Oka. It was also developed in Tim Warburton's group at Virginia Tech. And it's essentially abstracting things on two levels. One is on the host, the API, used to launch kernels, to allocate memory, to time kernels, but also the kernel language itself. So Oka has its own kernel language, which looks very similar to C, with just some additional directives. And we translate this kernel language at runtime to the target language, to the specific backend. And this way we can have one kernel source per kernel, but you may still have multiple implementations in that language simply because one implementation might work better than another on a specific backend, but at least you have it in the same language. But if you want, you can also have native kernels in the native backend language, and it will still integrate well into Oka. This is sometimes useful if there are some latest features of that programming language is not supported in Oka, or if there's some performance downsides of using Oka, although that rarely happens, but this option is there. I should also point out Oka is not doing any magic. It's just kind of a language translation when it comes to the kernel. I mean, it's not that it's being clever and all of a sudden it optimizes your kernels or something like that. It's really just a language translation and abstraction there. So this is one of the early simulations we did on Summit, but it illustrates two things. First of all, now with this new kind of GPU accelerated HPC platforms, we're able to do some fairly big simulations using a small fraction of the machine, right? I mean, here we compare a previous hero calculation on Mira, which was the number 3 in 2012. We used 33% of it. And this is at the strong scaling limit, meaning we try to increase the node count as much as we can in order to reduce the time to solution. And like 5 years ago, 3 to 5 years ago, we repeated that same case, and we only needed like 2% of Summit. And overall, we're still 3.5x faster, and the simulation consumed about 16x lower energy. So that sort of demonstrates really how this new machines offer lots of computational power, and at the same time we're able to speed it up. But the speed up, in fact, doesn't come that much from the hardware. This is maybe a 1.5x from the hardware. Keep in mind we're talking about the strong scaling limit, so that's kind of hard to improve the time to solution in that range. But if you really want to exploit the hardware, you also have to think about algorithmic changes. And here we trade, for example, a communication intensive part for a compute intensive part. And this way, we're getting overall a 3.5x. So this really illustrates two things. One is improving time to solution is challenging, right? 3.5x is maybe not something you would have expected. People talking about from one generation about factor of 10x or more. I don't think this is realistic, at least for our workloads. And the other thing it highlights is you have to think about your algorithms, otherwise, yeah, you cannot really exploit the additional computational power by these new technologies. Here are 4 application examples. I don't have the time to go into the details, but you may get an idea of how the code is being used. I mean, one is a COVID simulation, another one is an internal combustion simulation, another one is a is a pebble bed reactor where you have like 350,000 spherical pebbles, and all of them you have to resolve the boundary layers around them. So these are kind of things we can do with nekRS, and to sort of close on that end, the ECP EXA SMR team has recently performed one of the largest full core reactor flow simulation on Frontier. So it solved a coupled physics problem with neutron transport, and the mesh has about 350 billion grid points. And that simulation used about 9,000 nodes of Frontier, which is about 90% of the machine size. And we're nominated as a Gordon Bell finalist. And just to give you an idea about some ongoing work, we're working on documentation and training for nekRS. This is kind of our weakest part, and we realize this is really essential now to help the community to make the switch. So we're working on that. We're also working on tuning the performance for ANL's latest supercomputer called Aurora, which will come online next year, which is using Intel GPUs. And we're extending our mixed precision capabilities. That's also kind of a hot topic, and we're using already mixed precision, but there are many more areas where we want to explore this option if it provides any performance benefits. We're also working on wall models for RANs and LES, extended physics. So no longer we want to just be able to solve Navier-Stokes equation, but we also want to be able to solve MHD problems or chemically reactive flows. And together with some other collaborators, we're working on in situ visualization and also coupling to machine learning frameworks. Let me close my part with some trends and implications which are relevant for us. One big trend is all the major hardware vendors nowadays focus on this AI and ML workloads. Another big trend is there's a high demand for complex and possibly multi-physics simulations. And the implications to that, at least for us, is we only see moderate performance improvements when it comes to time to solution, simply because this AI ML optimized hardware might not translate into some substantial improvements when it comes to time to solution for our workloads, simply because the requirements for AI and classical HPC workloads is diverging. So basically, we have to live with the hardware which is being offered by the hardware vendor, having in mind that it's not optimal for our workloads. The other implication is we have a fast changing and unstable environment, right? If we think about the programming models and all that, and also all this new hardware technologies coming up, it's no longer that stable. And we also see a high demand for integrating with third-party applications, tool sets, and all that increases obviously the cost and complexity. And last but not least, the meshing and post-processing capabilities need to keep up. And this is quite critical. I mean, right now, we have an exascale ready solver, but the meshing and post-processing capabilities, which are out of scope for us, but obviously not for other projects. But currently, I don't think they're able or they're exascale ready. But this is a very obviously critical part of the workflow. And if we don't manage to keep up there, yeah, we cannot run any kind of meaningful exascale simulations. And with this, I want to close and turn over to Mattis, and he will share all the nekRS activities which are going on at Jülich.
Yeah, thanks, Stefan, for this very nice talk. I always say this that I'm very impressed about what nekRS is able to do, and all of these activities. Stefan showed a lot of activities also going on in the US, and I will now also put a little bit of focus on what is going on in Europe. And as we have some time limitations, I just pick one application case, and in this case, because CoEC is also part of this Code of the Month talk today, I chose some combustion case, which was also quickly shown by Stefan before, to just give a little bit of broader perspective also with respect to workflows that are possible with nekRS, because we know that if you might want to use the nekRS maybe in more industrial applications, it's not just about the pure performance and features of nekRS, but it's also about what can you also do this, what can you do with the code, and which workflows are possible. So let's for a moment talk about this so-called TU Darmstadt engine, where collaborators with us from ETH Zurich try to run the largest TU Darmstadt direct numerical simulation in the world with nekRS on our system. And obviously, running an engine, at the end of the day, even a reactive engine, it's not just you make a grid and you're good to go, but it is quite complex, because it starts with the grid, because you need to, you have a complex geometry, like with the valves of the engine, all of that stuff. So there's a workflow, how you do this, also with commercial tools like ISM and then TED2Hex. But then it also is, you need to have an initial condition. So they use like star CD with LES to have some initial field, which then can be used finally in the DNS and the compression stroke simulation. So as you see, nekRS is not cannot be just used on its own, but also within these complex workflows. And I think on the next slide we see also the results of this. So here we see the non-reactive full engine simulation with nekRS on the right. So you see the velocity magnitude and the temperature. And we have a RPM of about or of 2,500, and we computed 12 cycles of this engine. To do this, as you see also on the right, we have like moving meshes, but not just moving meshes, but we also interpolate in between meshes, because due to the stretched meshes of the moved piston, you have issues that the meshes become too fine. So we interpolate this, and then like the target, the biggest mesh has like about 9.3 million spectral elements, which results in about, for order 9, about 6.8 billion grid points. This results in about 44 terabyte data per cycle. And just to give you a perspective, it's about 0.27 GPU or million GPU core hours to compute this on our system. And here you have to know that we might compute the GPU core hours a little bit strange, because we kind of compute it based on the number of cores on the host CPUs of these GPUs. So basically, what is meant by this, you have each node on our booster has like 48 cores on the CPU side, and each of these nodes has like 4 A100 cards, and if you do the math, then you end up with 0.27 million core hours. So so you can run these simulation, and I always find them quite cool. It's looking cool how the turbulence and the tumble goes on, but obviously at the end we want to also tackle science or improve industrial processes. So you can do some analysis here. For example, I showed some pictures with respect to boundary layers and turbulence there. So you see, if we compare, for example, the boundary layers and the wall models with classical models, this are here the black dotted line. You see that in the DNS we found that, well, actually what you typically assume in the wall models, it's not too good for all of the operating points. Okay, maybe we move on. So we can run these very big simulations, but I know that for many industrial applications, it's also very important that Then you maybe can also couple your code with other codes. For example, here we have an example with OpenFOAM, because OpenFOAM, even though we probably all agree that it's not an exascale code, has a wide functionality in terms of different models. So you can, for example, use the field computed with nekRS at full scale, and then map this in a much smaller OpenFOAM simulation where you have many more models available to do study of different LES models, as here shown for a flame kernel simulation. So if you combine codes like this, also in your workflows, you can drastically reduce the time to solution, or even make workflows possible, which would, for example, not be possible if you only would use OpenFOAM. As Stefan already said in the beginning, nekRS is used for a lot of scientific discovery science, which comes also sometimes with the idea that it's a little bit hard to use. And we are fully aware that if you want to use a code with a broad community, it needs to be simple to be used. And this means like the code needs to be simple to use, needs to be documented. Stefan already commented on that. But it's not just that, it needs to also be easy to access actually the code on the required hardware. So we identified this also as one of the things which might be improved. So we developed Jupyter CoEC and CoEC, which is a very simple way of actually access all of our HPC resources in the browser, and in particularly also nekRS, which is precompiled on our system. And just to highlight some things, I don't go into too much into detail here. You then, for example, have much simpler visualization. You have all of the HPC resources, so also in future Jupyter. And here is just a demonstration video of how simple this is actually to be used. So you just have to browse. You go on the website, you have the browser, you register, then you log in, and then you just have the notebooks, and you're good to go. Here is a nekRS simulation. So it's now started, it's run, and then you can also quickly use, for example, a ParaView notebook in a server client session to then also look at the results. So there's really no excuse to say, well, it's difficult to be used, because everything what you see here can be used basically on your laptop and in your browser, in your favorite browser from everywhere. And that's also I know that's also often a major concern, how to actually legally get access to these systems. This is also quite simple via this procedure. So you might want to try it. You have the website here at the bottom. So with this, I want to quickly summarize what you heard, and maybe overall about nekRS, but also in my particular part. So I think nekRS, as mainly explained by Stefan, is really a true exascale code with already running exascale examples, has good performance at many different scales. We have a wide applicability, which with interesting applications from academia to industry, like boundary layers or convection processes or combustion or reactors. And it's quite simple to use, especially if you kind of use Jupyter CoEC. Just to give you also an idea what is possible with respect to support at JC. So we're always happy to give general support and help if you have problems with the code or with the system overall, help us powerful workflows, and also give assistance with respect to computing time, performance evaluation, scaling, and these things. And just to make this clear, so we will get the first European exascale machine next year. It will be called Jupyter, and well, nekRS is clearly also one of the target applications for this exascale supercomputer. And with this, I think I want to thank you for your attention of this webinar. And I think both Stefan and me are happy to answer any questions in case of questions.
Yeah, thanks a lot, both Stefan and Matthijs. And as you said, the floor is open for questions.